Hey, welcome back to part 3 in Models of Growth, and this is still to do with sequences. This one's called series, so let's have a look around the screen here and have a look at what we've got here. This is a little structure here in which the number of bricks in each layer follow an arithmetic sequence. And when might you want to add up all the terms of a sequence? Well, the answer is if you want to know how many bricks to make a wall, mate. Okay, and what about 0.7 recurring? This keeps going. It's a sequence of numbers. You would want to add up an infinite number of these fractions to come to the actual value of 0.7 recurring. Well, you can't actually do that. But can we estimate it mathematically? What about down here? Hang on, we'll just get rid of this. What about down here? Would we want to add up the terms of this sequence? I don't think so, because I think what we've got here is we're multiplying by 1.03, like compound interest, the original plus 3%. I think that's what that is. This is times by 1.03 again. So would you add all these up? No, they are what we might call running totals. This is the total since the beginning, and so on. So your bank's not going to give you the amount of money at the end of the first year, second year, and so on. You've left it in there and it's grown. So it wouldn't be appropriate to add up all the terms of that sequence. What about this here? It's a bouncing ball thing. We'll look at that later. The time taken when a ball is dropped and then it bounces up a certain proportion of the height each time. So this is a decreasing sequence. What is the total time that it takes? Here you might want to add up the times for all these transitions of the ball up and down, mightn't you? Okay, so think about that. When is it appropriate to add up terms of a sequence? And when you do add up terms of a sequence, they come up the top here, it's called a series. So a series is the sum of terms of a sequence. Okay, come on down and let's have a look at the definition here from Hayes and Harris Publications. So grab their book there. A series is the addition of terms of a sequence. So that's a series because it's got a plus sign between them. It's a result when all terms of the series are added is called the sum. So when you have things added up, you'll find the sum of them. So we would write it perhaps like this. Okay. Let's have a look at some elementary exercises in understanding the idea of a series. So here's a sequence. Write down an expression for Sn. So this is the sum of, as usual, n terms. So here it would be 1 squared plus 2 squared plus 3 squared, just recognising that these are squares here, plus 3 squared plus 4 squared up to n squared. All the terms are perfect squares. So the sum of one term is just 1. Sum of 2 terms is the sum of these two, which is 5. Just as a notation here, thing that we're getting into. Sum of 3 terms is that, so that's 14, and so on. So all terms here are perfect squares. We're going to just add them up. That's the idea. All right, let's do some. So here's some for you, 2b1. And I want you to pause the presentation, write down the expression for Sn, and then find S5. Sn is just 3 plus 11 plus 7, and then add up S5. So S5, well, that'll be an extra term needed. You'll have to work out what the next term is in there. So good luck with that. Anyway, pause it and have a go, and I'll show you the answers now. So there's our answers. So just check it out there. It's a fairly simple idea, isn't it? It's the sequence stuff extended to adding up terms, and that's called the sum of a series. Sum of terms of a series. All right. What about going back and looking at the special ones we looked at before, where there is a pattern? Okay, so the patterns that we have looked at basically were arithmetic, geometric, and Fibonacci. So let's have a look at the terms of an arithmetic sequence, and if we're going to add them up, so this is the sequence with commas. A series is when we are suggesting we want the sum, and we've got plus signs between them. Okay, so let's see if we can do a derivation. Is there a formula that we can use to quickly do the ones with a pattern? So first of all, what are you doing? You're finding the sum of n terms. So the first term arithmetic series is that. Then each one goes up by d, as you know. So then you have a last term. Let's say this is the last term. The term before it is that last term subtracting d, and the term before that is the last one subtracting 2d, if you like, coming in from both ends. Now what have we done here? Have a look here. We've reversed this line around and put the last term first and the first term last. Okay, so now what do you notice if you add up these two lines? So Sn plus Sn will give two lots of Sn. And this is A plus L. And when you add these two up, we get another A plus L. The plus D and neg D cancel out, if you like. And here, the 2D and neg 2D cancel out. This is very much something that Gauss did when he was a boy, to sum the first 100 numbers. I might tell you that story in a minute. So you've got n terms, and they all came to A plus L. So we've got n lots of A plus L. So the sum of n terms is divided by 2, n over 2 by A plus L. So that's interesting. And we could go further. What if you didn't know the actual last term? It was a 50th term or something. So what would the last term be? Well, we know a formula for every term. It's A plus n minus 1d. So the last term would be that. So the sum could be changed to n over 2, A, instead of the last term, A plus n minus 1 times d. We could have that. And so that comes to n over 2, 2a plus n minus 1d. Okay, we could do it that way. Okay, so what about looking at those two forms now? So come down and have a look at this one, n over 2, 2a plus n minus 1d. Okay, so that's what we've got. Hang on, I'll just correct this up here. I've written this wrongly. A plus, there's a plus missing in there. Okay, so we could use this if we know the first and the last term. Or if they say sum the first 50 terms, we'd use this one and actually calculate the 50th term by putting n as 50 in there. All right, so let's have a look at practicing those formulas now. And here's an example from Hayes and Harris. So sum these to 50 terms. The first term is 4, the difference is 3, and you want 50 of them. So S50 is 2a plus n minus 1d, that formula. So it's n on 2, 2 times a, n minus 1 times d. So you get a total. So it's a fairly basic idea now. So let's have a look at you doing some. So 2b2 here, using the formula. Okay, see if you can sum those terms. Right, pause it, have a go, and I'll show you the answers now. So there they are. Let's move on, see what else we can do. Here's another one. This time we're starting with a negative number, but you can see the common difference is 7. So we list them out. The first is neg 6, common difference is 7, and this time they give us the last term. So we can use the shortened formula, and that is this one over here. 22 over 2, first plus last. But you've got to know the last term using this method. And also, we still have to work this out because you've got to know the n here, the n number. So here we're going to say the last term is 141. So therefore, putting in A and the difference, you can backtrack and find that that last term is the 22nd. And so that gives you the number to go in here. Or you could go to this formula here, and once you've got n as 22, put that in there. So the last term formula still needs an n value. So you end up having to work that out anyway. So have a look at backtracking with that and see what you think. I want you to practice that now. So come down. Here are some theoretical problems, and there's our bricklayer problem again, and others of a practical nature. So I want you to really think about that, and particularly these later on, if you're going on with maths, to look at some proofs there. So I'll scroll down here, and then you can pause it and look at the answers. So there's the first 5. Let's look at the rest of questions 6 and 7, 8 and 9. Okay, so there's some interesting questions on the end. And if you're into this and want to continue with maths, I really suggest you have a go at those. Okay, well, pause it, have a go. I'll show you the solutions now. They're coming down here. There are some answers there. It doesn't really show you how to do those harder ones, so you might have to check with your teacher and classmates and discuss some of those harder ones. All right, let's go on to the geometric one, the other one that we know a pattern for. Geometric is first term, and then you times by r, and we're adding them up because it's a series, then by another r, etc. And coming in from the other end, the last term is ar to the n take 1, the one before that is ar to the n take 2. All right, so we're trying to sum that. Is there a trick we can use here? Let's have a look. Here's the trick. You get the sum, and if you multiply it by r, they end up all having an extra r in them, and you end up with ar to the n. Okay, so that's the trick here, and then we're going to do some subtraction here. So if you put rsn in the top and sn here, and we take them away, rsn take sn would be this line minus this one, and these terms go out. Okay, so they all match up, so subtracting them just leaves you with ar to the n take a. That's the trick there, an algebraic trick. And if you factorise this side, Sn out as a common factor, r take 1, take a as a common factor, r to the n take 1. And then what can you do here? You can divide both sides by r take 1, and you get the formula. Now, this form is handiest when r is bigger than 1, so you end up with a positive in the bottom line. Or if you multiply top and bottom by neg 1, you get this form. And this might be more convenient when r is a fraction, because you get a positive number in the bottom line there, 1 take r. Okay, so you obviously with a proviso, that's what PV stands for, with a proviso that r is not equal to 1. Obviously, r is equal to 1, all the terms would be the same, and the bottom line there would be undefined. You can't divide by 0. All right, you need to do some here, so I'll give you a few little ones to have a look at. First of all, an example. This is geometric with a ratio of 3, so we want to sum the first 12 terms. So put down the formula we've just found. So then putting in a is 2, r is 3, take 1, over 3 take 1, and we're getting big numbers here. You can see if r is bigger than 1, the size of the term gets quite large, and so your sum is going to get quite large as well. Okay, all right, so are you ready? Just using that formula now, and you can use this formula for r bigger than 1 or less than 1. It doesn't matter, just watch the fact that if r is less than 1, this turns out to be a negative. Don't drop the negative sign on your calculator. All right, let's have a go. And so we've just got a few examples here. 2b3, find the sum of the following series. So just going through the formula, might have to watch this one. What's the r here? Remember, the r is any term divided by the one that came before. So you might have to just watch that there. Okay, have a go, and I'll show you the solutions now, or the answers at least. Here are some answers for that one. All right, well, what you want to do, of course, is say, well, Huddy, when is this going to be useful to me? So let's have a look at using it in some situations. First of all, we'll do another one here with a ratio which is neg a third here, multiplying by neg a third each time. And so it is geometric. A is 9, r is neg a third, and we want to sum it to n terms. So this is a general formula. So here we're going to n terms, so put in a, we put in our R, and 1 take R, and so we come up with this sort of formula. And you can't go further because it depends on n. And that's what this guy says over here. So obviously with a negative ratio, if you raise it to an even power, it would be positive. To a negative power, it would be negative. Okay, so it depends on n. So we simplified a little formula there, and we could discuss that for large n. Okay, I want you to come down and have a go. Here's some questions. So there's some standard ones up here. Just watch the R's in here. And we're looking at general formulas here. And then let's have a look at some applications here. So coming down, question 3. Question 4 is an interesting one. Okay, might have to discuss that in class with teacher and other students. And then question 5. Okay, here's the ball one from before. It takes 90% of the time to rebound to its new height. So we're looking at the t situation here, 1 second and then a fraction of that and going down. Okay, so you might have to consider an infinite series here. This links up with these parts up here in the preceding question, where you're looking at n becoming an infinite number of terms. What does the sum approach? All right, have a go at all of those and I'll show you the answers. Okay, so there we go. And you might have to discuss some of this work, things like this, as to how that works out. All right, well, that's the end of the sequence series unit. That's one way of modelling growth, isn't it? And in the further presentations, we'll come across other ways as well. But at the moment, it's cheers for now.